Good morning, bom dia, subadaya. Welcome to the fourth edition of the International Conference on Direct Digital Manufacturing and Polymers. My name is Jeffrey Mitchell. I'm one of the co-chairs of the conference. I particularly welcome Professor Rui Pedrosa, President of the Polytechnic of Leiria. I also extend a warm welcome to our partners at Karnataka University in Dharwad, India. It's timely for all of us to remember that the crisis raised by the pandemic still rages in many parts of the world, not least in India. And so our thoughts are with you all. So thank you for joining us. I'd like to draw your attention to the sponsors of the conference, in particular the platinum sponsors, Periplast, Multipo Group, Moldwelt. These are three major companies in the Leiria area. And we also acknowledge the provision of a prize for the best presentation by the Journal of Manufacturing and Material Processes, which is an open access international indexed in Scopus journal, which is hosting a special issue for ICDDMAP 2021 titled Developments in Direct Digital Manufacturing. And all presenters over the next 3 days are invited to submit a manuscript to this issue with a 40% discount on the article processing charge. So we thank these and all the sponsors for their support. Today, it seems a long time ago that we met in Dharwad in 2015 to inaugurate the first edition of this conference. And for those of us from Portugal, we experienced at first hand the vibrant welcome and the culture of India. It was really a great occasion. A lot has happened in the world in the intervening 6 years. What was an emerging idea or concept in 2015 of direct digital manufacturing has flourished into practical activity. If we drive around Marina Grande, where CDRSP is based, today we will see many buildings signed as additive manufacturing centers. So this means we're rapidly developing new concepts, knowledge, and expertise, which is leapfrogging the formal learning stage to become part of lifelong learning for both teachers, researchers, and end users. And I think this represents a challenge for higher education institutes all around the world. Today, compared with 2015, both institutions have new leaders. And today we welcome Professor Gudsai, Vice Chancellor of Karnataka University, who will join us by video clip. And also we welcome Professor Rui Pedrosa, President of the Polytechnic of Leiria. The Center for Rapid and Sustainable Product Development, CDRSP, has moved to a purpose-designed building in the Zona Industrial in Marina Grande. The Polytechnic of Leiria and Karnataka University have signed a memorandum of understanding, and numerous papers and book chapters have been published. CDRSP itself has been rated as excellent by the international panel appointed by the Foundation for Science and Technology in Portugal, and they evaluated CDRSP to be the best research unit in Portugal in mechanical engineering and systems engineering. This year, quite recently, a consortium of research units, which includes CDRSP, was awarded laboratory associate status, one of just over 50 institutions to be awarded this status in Portugal. And of course, many highlights have resulted from individual success with funding, projects, presentations, scientific papers, which have a strong impact on society. Today, we're very pleased to be joined by Professor Siram Ramakrishna from the National University of Singapore, who is also the Honorary Everest Chair at the Mardan Bandaraya University of Science and Technology Development Board, which is a really exciting project, I think, in the university a new university in the mountains of Nepal. And we can remember that Professor Ramakrishna was the opening plenary speaker at the first edition of ICDDMAP 2021. So it's now my pleasure and honor to invite Professor Rui Pedrosa, President of the Polytechnic of Leiria, to give his welcome.
Good morning to everyone. It's a great pleasure for me to be here. I want to thank the wonderful words that the chair of the conference, professor and researcher Geoffrey Mitchell, give to us, and to start this open session. Of course, for the Polytechnic of Leiria, it's a great pleasure to have this joint international conference with the University of Karnataka. Of course, I want to greet Professor Gudasi, the Vice Chancellor of the University of Karnataka, because with me, we have both of us a great pleasure to be the patrons of this international conference. Of course, I want to also greet with a huge pleasure the both presidents of the conference, Professor Madhavappa and Professor Nuno Alves, which is the director of the CDRSP, our excellent research center linked to the direct digital manufacturing. Of course, I want to greet all the chairs of the conference, the organizing committee, the scientific committee, all the professors, researchers, and professionals that will share with us outstanding research that for sure will not only give to us solutions for the several challenges that we have through the direct digital manufacturing, but of course will open new opportunities for the research and our R&D projects in this topic. I want to greet all the technicians, researchers, students that are with us. I want to join to the words that were given by Geoffrey Mitchell with concerns to this pandemic situation that we live worldwide. And in the beginning of this year, Portugal was the worst country in terms of the COVID-19 cases in terms of the pandemic situation. We know that nowadays India are not in a good condition related with the pandemic situation. So I want to join to the words that are given by Geoffrey Mitchell in related with this situation that India lives today. Just one or two topics. First of all, I want to really thanks to all the scientific committee, to all the chairs, to the efforts that all of you did to guarantee that we have this very, very important international conference on direct digital manufacturing in the worldwide context. This is one of the outstanding international conference in the world in this joint venture between the Polytechnic of Leiria and the Karnataka University. The second thing that I want to mention is that it is not only the quality of the research that all of you will share and discuss during these days. Is also the connection to outstanding international papers that you will publish and that you will share in the worldwide context. Third and finally, I want to finish, but and to finish, I want to say something that for me is it's very important, because nowadays we need more and more this kind of international collaboration, because we really need higher education institutions. We really need research centers. Without, we really need a society without walls, because the main global changes will only be overpassed with this international collaboration, with this sharing research, and is exactly this that with this conference we are doing. I want to strong and highlight this idea, because during this pandemic context, which is that show clearly that science and knowledge are global with no borders, and is completely dependent of national and international networks that need more and more contributes in a multidisciplinary co-creation context, and only with these global science and knowledge networks will be possible to overpass this kind of global challenges, just as this pandemic situation that we live today. So thank you very much to all of you, and please enjoy these full days of science inside the International Conference on Direct Digital Manufacturing and Polymers. Thank you very much.
Right, thank you very much, Professor Pedrosa. Now we move to have a short video from Professor Gudsai, Vice Chancellor of Karnataka University, with his welcome. Renato.
Hello, good morning everyone. Mr. V. Pedrosa, President of the Polytechnic Institute of Liria, Professor Nuno Alves, Director, Center for Rapid and Sustainable Product Development, Polytechnic Institute of Liria, Professor Mahadev Diganawar, the Chairman, Department of Chemistry, Karnataka University, Dharwad, Conference Chairs, Professor Jeffrey Mitchell, a well-known and very familiar face here in Dharwad, Professor Arthur Matthews, Professor Kamble, Professor Vedamurthy, conference speakers, delegates, ladies and gentlemen. Good morning to you all. It is my pleasure to address all the participants for this 3-day international conference on direct digital manufacture and polymer 2021 at CDRSP, that is Polytechnic Institute of Leiria, Portugal, in collaboration with Karnataka University. I welcome all the eminent speakers and guests from all over the world who have come with different backgrounds to share their knowledge and experience. I deem it an honor that the Center for Rapid and Sustainable Product Development, Polytechnic Institute of Leiria, Portugal, and Department of Chemistry, Karnataka University, Dharwad, are jointly organizing this international conference on direct digital manufacture and polymers. At this juncture, I am happy to recall that our university had hosted two such conferences in the past. The first one during October 2015 and the second during February 2019 with the active participation of CDRSP. Indeed, it is a great pleasure to say that both the conferences were highly successful, and also I take this opportunity to thank CDRSP, Institute of Leiria, Portugal, for selecting Karnataka University for the Best International Partnership Award in 2017. Thank you so much for that. It is needless to say that this modern world is ever changing and ever growing to meet the challenges posed by the globalization. These changes and developments are more noticeable in science and technology and medical sciences. Advances in these fields have to march hand in hand with a serious concern for ecological balance as well. Further, there is a demand for evidence-based and authoritative theories that will be accepted by the society. Hence, in this global scenario, a broad and well-equipped platform is required to further the frontiers of knowledge and ensure that it reaches all sections of society. I hope this conference will create a platform to establish interactions between academia and industries, to establish new industries and research collaborations. I hope this international conference will be a historic and meaningful academic program. I hope this conference will bring together a panel of highly accomplished experts in direct digital manufacturing and polymers. As I understand, direct digital manufacturing is an emerging technology that is set to revolutionize the manufacturing process and thereby produces complex shaped objects directly from a digital definition without the need of expensive tooling or the molds. This enables mass customization, which is of particular importance in medical and engineering devices. I understand that around 200 scientists, doctors, and industrialists from different parts of the world are expected to participate in this conference. I learned that organizations have instituted the best paper presentation awards to encourage and recognize which is highly appreciable. Congratulations for that and thank you so much. I request all the participants to actively involve during this 3-day conference and explore the discussion and deliberations of the forum. As we all know that the whole world is facing the consequences of the COVID-19 pandemic, and hence this is the right time for the scientists to work on this, and I expect some deliberations on this issue from our learned resource persons in the conference to make this world a better place for living. I congratulate the organizers for organizing such a meaningful event during this crucial time. Thank you very much for allowing me to share my views at this juncture. I request all the speakers, participants, and organizers to stay safe and wish you all the best. Thank you so much. Namaskar.
Thank you very much, Professor Kutsai. Before we start the session, I would just remind all participants that a feature of the ICDDMAP conferences is the opportunity for the audience, the participants, to vote for the best presentation of each session. The winner will receive a certificate and a discount on future registrations at these conferences, and an international panel of judges will review all the winners and select as the winner of the best presentation of the conference, who will receive a prize of €500 from the Journal of Manufacturing and Material Processes. And so during each session, my colleague Renato will place a URL in the chat box of Zoom. And before you leave the session, if you could just take a minute to go there and cast your vote, it would be very good. So now it's my pleasure to introduce my dear friend and chair of the morning session, Professor Mahadevappa, chair of the Department of Chemistry at Karnataka University. Over to you, Mahadevappa.
Hello.
Hello, ಕೇಳಿಸ್ತದ?
Hello. Sir, good morning to everybody.
Thank you.
Good morning to everybody. I personally thank Professor Rui Pedroso for conducting this conference in Liria, that too in IPL campus. So I also thank the Jeffrey Mitchell, Nuno Alves, Dr. Arthur Matthews for conducting this conference so nicely. I take this opportunity to welcome Professor Sriram Ramakrishna to give a first plenary lecture in the first day. So I take this opportunity to thank all the staff of the CDRSP arranging this conference so nicely and meticulously. Thank you very much.
So Jeff, it's my turn?
Yes, yep.
Okay, good. Well, let me say that it's a wonderful delight to see all of you after the first successful conference a couple of years ago.
Excuse me, Sriram sir, shall I introduce first, I think?
Okay, sure.
Yes. Sorry for the inconvenience.
Sure.
It is a great privilege for me to introduce Professor Sriram Ramakrishna, Director of Center for Nanofibers and Nanotechnology at the National University of Singapore. Thomas Reuters recognized him among the world's most influential scientific minds. Sriram Ramakrishna is a highly cited researcher. He is one of the top 5 scientists of Singapore and the most cited engineer in the history of Singapore. He authored 6 books and more than 750 international papers published, which attracted more than 122,000 citations, and H index is more than 161. His research outcomes have been translated into many products and available in several countries. He is an editorial board member of 10 international journals. He is an UNESCO expert on nanotechnologies. He is an elected fellow of Royal Academy of Engineering, UK, Academy of Engineering, Singapore, National Academy of Engineering, India, Asian Academy of Engineering and Technology, Institution of Engineers, Singapore, American Association of the Advancement of Science, ESM International, American Society for Mechanical Engineers, American Institute for Medical and Biological Engineers, Institution of Mechanical Engineers, UK, Institute of Materials, Minerals and Mining, UK. He has received many awards and recognition worldwide. With this brief introduction, I have a great pleasure to welcome Professor Sriram Ramakrishna to give his plenary lecture on this day. It is a morning to Portugal. It is a midday to India. So with this, I once again welcome Professor Sriram Ramakrishna. Thank you very much. Now it is your yes.
Thank you, Professor Mahadevappa, for your kind, heartfelt introduction. I also like to say my thanks to the organizers, Jeffrey Mitchell, Nuno Alves, and Nuno looks always younger than me. Nuno, what's the secret? And of course, Paula and all others who are organizing this conference. Let me share my screen, then I will start my presentation. Okay. Can you all see my slides?
Yes, yep.
Very good.
Yes.
Well, thank you so much. I've been given about 40 minutes. So I start my presentation now. I have close to 95 slides, but the idea is that I focus on most important information. But I'm very happy to share a copy of my full presentation if you approach me directly at this email, or you could also approach the conference organizers and you can get a copy of my full presentation. Again, I like to begin and say that this international conference on direct digital manufacturing and polymers is very timely. It was conceived several years ago. There was a first successful conference, and we have the series of that similar conference now. So one of the key word there is polymers. I like to give attention to the polymers or plastics, connecting that to what is happening around the world in recent times. So I think as an introduction also, I'm a member of UNESCO expert group on sustainability and universities. We are looking at sustainability and future of education, higher education. Let me say that I come from Singapore, and I was introduced by Professor Mahadevappa very kindly. Singapore has been the forefront of sustainability. If you see the news clipping that just appeared yesterday, Dr. Jonathan Pershing, he's an advisor to the US government, and they say some of the practices Singapore is doing is worth emulating. Similarly, we know that many cities around the world are affected by climate change. Mitigation strategies include using renewable energy, improving the green spaces, green transportation, and enhancing recycling. On the right side, I also have what pulse of a young generation that are attending this conference. Some of you might be the future billionaires, and they are already investing based on ESG, environmental, social, and governance, based on which they are actually investing in companies which are deemed to be more progressive in the coming decades. To give you a number, more than few $1 trillion are now invested based on the ESG principles around the world. So it's one of the major direction that's happening in European countries, Far Eastern countries, as well as US and Canada. Well, if you still want to have the message very loud and clear, in addition to pandemic, which has been highlighted by Jeffrey Mitchell, rightly so, that has affected hundreds of millions of people, also saw several thousands of deaths, and also that is still has not come under control. But there is a general perception beyond COVID-19, climate change is another major threat for the survival of the humanity. Here is a projection. If these ice that melts in Arctic, that could raise the sea levels by 7 meters. And that means at least 1/3 of the human population that live near the coastal areas will be threatened. That includes Singapore. So that subject, sustainability, is very important. And I'm fortunate to be with the people like Professor Walter Sahal, who is the father of circular economy, along with all other eminent thinkers in the area of sustainability and circular economy, where I'm a part of the discussions globally. So some of you, if you are interested in this topic, this is 2 books we have written. One is on Introduction to Circular Economy. Other one is Sustainability for Beginners. You could get a copy of them. You would understand deeply what I'm about to present or emphasize in this lecture. On the right side, there is a book we just published on additive manufacturing, which is very similar to, very closely aligned to the direct digital manufacturing, which is one of the focus of this conference. Now, let me begin by saying why sustainability, circular economy are important, because materials related emissions are nearly 25% of the total greenhouse gas emissions that are emitted by human activities or anthropogenic activities. Now, these are the details based on which particular industry, based on which particular material class, based on which countries there are major contributors for emissions related to the materials economy. And here is specifically focused on subcategories, and you notice plastics is one of the important material class that contributes to the overall carbon emissions. I remember, and I asked Jeff, is this topic of interest? Jeff said that's exactly of our interest, what we are doing. And in addition to emissions, there is one more important aspect, which is the waste generation. To have a sense of waste generation, in the year 2020, if you compare total manufactured material on planet Earth, that is almost same as the total mass of all the living beings on the planet Earth. I just want to remind you, as far as human knowledge is concerned, living beings still only exist on planet Earth. And right now, all the manufactured goods, the volume and weights, they actually equal to or even more than all living beings on the planet Earth. So they are leading to excessive manufacturing consumption, leading to different types of waste, biodegradable waste, non-biodegradable waste, and hazardous waste. And now this is a biodegradable waste like food, which we throw away, along with the plastics that we use for packaging them. Similarly, non-biodegradable waste, and then you also have a hazardous waste. So there's different types of waste streams that are generated because of the way we are living. Now, I take these emerging concepts and go deeper into the context. This is a diagram put together by me, looking at the human history over the last 100,000 years, and a materials journey along with that. And obviously, 1500s, we have rubber. Before that, natural materials like cotton, silk, and leather. More recently, we have from 1950s, various kinds of polymers that have been invented and manufactured in millions of tons of quantities and used in several millions of products. And question is, if we move forward, what would be the future? I fundamentally believe there are two important directions. One is intelligent materials. That means the materials will be intelligent, will be made intelligent. Second one, materials will be low carbon. That means I will define these things in my next slides. Intelligent materials, I define it as a material expected to have the ability to be aware of external stimuli, learn from it, to optimize own responses and behaviors to achieve certain goals and choices to make, so as to improve their own application performance. And there are already evidences, for example, in this case, we use a variety of fibers. We make wearable devices like PVDF, which is a polyvinyl fluoride, as well as many other fibers. We spin them and we make wearables like rings or clothes. And we monitor the vital signs of the people like heart rate, respiration rate, glucose level, temperature. Also, we generate energy from the body movements. So this is the cutting edge concepts, how we use polymers manufacturing, produce new products. So if you notice, the wearables is becoming an important topic. Apple just released an application where it talks about giving and monitoring vital signs of the people. And in the situation of COVID-19 for remote health monitoring, many of these devices are very helpful. So I do not have time, but I think I will try and play this one. If you see, we use some of these polymers. We make a tactile sensors for robotics. In this case, our research engineer demonstrating to you a robotic hand, which is touch sensitive. So when he touches it, it automatically comes to a stop. Now imagine how if robots trying to help with the people with advanced age, they have disabilities, or young people with certain compromised mental abilities, such devices will be extremely useful. So that's a kind of an example to show you, right? So you can imagine now grippers, which are a lot more tactile sensor-based approach. And these are, again, electrospun nanofibers. We convert them into these sensors. The point now is, if you look at those kind of sensors, which are very advanced, you look at their greenhouse gas emissions, and you look at the energy consumption, based on the material choice, you actually get a different kind of results. So obviously, moving forward, when you are making these products, they would become one of the important criteria. Now I define another next concept is low carbon materials. So low carbon materials are materials necessary to develop low carbon economy. Low carbon economy has been announced by USA, European Union, China, Singapore. They all say that by 2050, they would want to be carbon neutral. Many multinational companies announce the similar goals. So obviously in a low carbon economy, you want materials to have a low embodied carbon per unit of material, or in other words, low carbon footprint and a higher material circularity. So there's a lot of details. I would not go into those details, but that's how you can achieve low carbon materials. And so far on the right side, we've been pursuing a linear economy last 150 years. But moving forward, we will be pursuing circular economy, be it advanced manufacturing, advanced materials, or large-scale services. So this is how different concepts, so as to reduce the total carbon in the material, so as to reduce the embodied carbon in the materials. And now this is a polymer conference and manufacturing conference. I thought I will show you a periodic table which we prepared with the different polymers, widely used materials, and I have shown two important numbers. One is the embodied energy, another is the global warming potential. You could see different polymers, how they stack against each other. Now the case study. This is a work we are doing with our collaborators in University of Toronto. Transportation is one of the major source for emissions. And if you want to reduce the emissions in the transportation sector, you might want to look at a lightweight materials. In this case, a composite materials where they have introduced natural fibers into the composite system and reduce the weight so as to reduce the carbon footprint. And you see the numbers, see there are specific components in a car. And these are the results. Actually, you can see a hybrid car with these composite materials manufactured with advanced manufacturing techniques that involve some other additive manufacturing methods. You reduce the overall carbon footprint. So now, I'm now going deep into the plastics. And anyone familiar with plastics would know the history. Well, one could predate it to 1284. Natural plastics started being used by the human beings. And moving forward, a variety of synthetic plastics have been made and used in a variety of modern applications. Now, that's a number of plastics by usage, packaging, building and construction, and textiles is a major area. And these are the different geographical regions which are really producing them. What's the issue? Generally, plastic has been seen as a hero for the last 50 years. But in recent times, because of the pollution as well as emissions associated with them, some other communities worldwide see them also as a villain. Why is that? Because we have produced more than 6.3 billion tons of plastic, but only 9% of them are recycled. In other words, 90% of them are either landfill or burnt, which are causing subsequent health-related issues. And here is with COVID-19, as Jeffrey Mitchell and others mentioned, COVID-19 also saw surge in the use of plastics in variety of PPEs so as to protect the populations as well as the medical community. But the outcome is, while we are protecting the people, we're also generating a lot of hazardous waste, which lead to the problems of the waste pollution. In this case, it shows what is the half-life of a typical plastic that is thrown away, either in landfill or in oceans. It's hundreds of years. And that some of them eventually get as a microplastics, absorbed by the marine organisms, eventually ingressed by the human beings, affecting their health. One of the issues is microplastics also threat male fertility. That means their ability to reproduce themselves would be compromised because of the microplastics and other chemicals, additives that are used in plastics. So obviously, the world is concerned. There are lots of different guidelines are coming worldwide. These are a repository of articulations. I teach this subject at the National University of Singapore. That's why I just put one slide giving you the whole summary, but I don't think I can finish this in the next 30 minutes, so I'll skip all of them. So the point here is I want to emphasize, especially the young people, those who are looking for economic or entrepreneurial opportunities, it's a good area. So here is the plans by different countries in East Asia, Southeast Asia, where they have plans to regulate or change the plastic consumption, electronic waste in the world. So interestingly, apparently only 20 companies would contribute to more than half of the plastic waste that is generated in the world. So obviously, if you can work with them and find a solution, you would be a very successful entrepreneur. So those of you now interested in the real technology, I'm now taking you through the recycling technologies, mechanical recycling, chemical recycling, and pyrolysis. And this is basically the details in terms of a chemical recycling, what we normally do. And these are typically plants look like that. And some of the wastage still happens as you are doing chemical recycling. Some effluents are coming, requires further innovations. And these are the definitions between mechanical and chemical recycling. we established a plastic recycling association in Singapore. You could see me with my partners from Germany and other countries. And we are now going to investigate mechanical recycling, chemical recycling with a focus on PET. PET is a very interesting material, and Anti-Plastics is another company. We look at chemical recycling based on ionic liquids that will promote better, improved, low carbon potential recycling of plastics. And this is all the details, and these are the other similar kind of technologies elsewhere in Europe as well as Japan, and some other details. And more advanced new ideas, they're using natural enzymes, and they're creating bioreactors to do the recycling of the plastics. It's much more environmentally friendly. And these are the details, okay? The question is, there is a concern about the standardization and recycling technologies. The materials that are recycled are not yet highly receptive by the other recyclers. One of the issues is the standard and quality and endorsement of the collected, sorted waste materials. So you can think of a blockchain technology, which now you can do the watermarking of plastics. In this case, you use polymer sequences, and then you actually can create a watermarking. So we developed carbon dots, where we could use a particular fingerprinting of plastics. We can introduce them into the plastics, and then you can label them with encryption, so that only certain people can know what exactly this particular plastic. So it's extremely helpful when you are trying to collect the plastic, segregate them, automate them. So this is the future. If anybody is interested in recycling of plastics, I advise them to think about watermarking of plastics, which is very essential. So then other ways is collection technologies. There's other avenue is substituting existing plastics with a renewable source plastics. This is a biosourced, and this is a comparison between synthetic polymers and bio-based polymers. And you can also use them as a mixing with other matrices. And they're also fully biodegradable alternatives like Eminisol Eco. They're introducing these kind of polymers into the market. You can also think about designing them differently. I know when I visited Nuno's center in Portugal, they are thinking innovatively how to design different products. So this is how you can think of a biodegradable based materials, but new way of packaging that can be used by the food outlets like McDonald's, KFC, and other companies. We do that in Singapore. You can see them. And that's how bio source-based polymers and circular economy. Well, while the story is good, recently we just heard that IKEA has to recall these PLA-based plastics because public are concerned about safety issues. Some of them are broken. So if you are jumping into bio-based polymer alternatives, you have to be mindful about their physical, mechanical properties, and also the recycling involved changes in the properties. So that's very important. So now, then you can increase your ability to further improve the innovations by upcycling. You can think of 3D printing, for example. We are doing with a PEEK, polyether ketone. We are doing that in Singapore in my laboratory with the additive manufacturing. So we can look at different ways of improving the interlaminar strength of a 3D printed PEEK material. And Sharp company, like other companies, are looking at upcycling plastics. So that means not only recycling, but they are looking at upcycling. So if you can upcycle very well, PET is a fantastic material for upcycling. For example, PET waste can be used eventually for food packaging, which requires a higher standards. Now, you can also add additives like a coffee extracts after, say, Starbucks. There's a lot of coffee after post-filtration, the waste will be thrown away. You could think of improving as a fire retardant materials. So, or you can even go to the basics of polymers, redesign the polymers and make them circular plastics. That means they're easy to recycle without much of additives. So this is a new concepts happening. So you can imagine a future low carbon products, low carbon services, and low carbon materials. So now I bring the concept of circularity. I sit in this ISO committee, which is involved in ISO 59020, which is focusing on circular economy of plastics. So where we define what is circularity. Circularity means it's a state of a system or organization of product where resource flows and values are maintained while benefiting the sustainable development. So you can have a metrics. You can analyze either product or a service or an organization using that methodology. And you could have indicators like this, for example, resource inflows, waste and emissions. You can track them based on which you can compute how circular is your material, how circular is your product. So there's already softwares available by certain companies in Europe, consulting companies. You can take a look at them. They're already providing such thinking. So now I'm going to give you a case study, and then I will end it, so that you know it is not just research at the university, is actually an industrial adopted methods. April is one of the large producer of textiles in Singapore. It's called Royal Golden Eagle. This is how they subscribe themselves to the UN Sustainability Development Goals. Now, what you see here, they like to see 90% of energy they use comes from renewable sources. They reduce carbon emissions by 25%. They like to see 50% increase in the production capacity and also 20% of recycling of the waste plastic. So you could see this is what it translates. So if you are working with companies, either in Europe or in Asia, these companies are beginning to think how to collect waste, plastic waste, and recycle them. They have targets like 10%, 20%, 30%, eventually 100%. So if we can come up with an ideas, I think that would be very good. In this case, this is a company I am closely interacting. It's a large company, and they have a target of 25% reduction in the certain resources utilization and 20% recycled textile from viscose fibers. Similarly, Sateri is another company, one of the largest producer of viscose in the world. And this company, again, we work, and you see them, viscose, lyocell process, recycled fiber, and yarn. They're used in many of the products in the human applications. So the point is, any of these technologies require certification. There's lots of good certification, third-party services are available. We should be aware of them, and we can approach them for validation. Now, I'm coming to almost near to the end. I'm showing you this company, Sateri. If you see them, they're looking at climate ecosystem protection, closed loop processes, innovation and circularity, and inclusive growth. Now I'm going to give it. So by 2030, that means about 9 years from now, they would like to have close to 30% reduction in greenhouse gas emissions. And they like to have a closed loop process in terms of the textile products primarily made of viscose, which is one of the combinational polymer. And by 2050, they like to reach net zero emission. These are large cap companies. And this is how a recycled materials is already in the market. It's called Finex. It has a 20% recycled content. So moving forward, that would go up to 50%. So now you see the story where I'm emphasizing plastics, sustainability, and circular economy. And this is how you could actually further improve the process, in this case, lyocell process, where you have 100% solvent recovery. And here is a circularity analysis where you look at by 2023, this process will have 50% recycled content. By 2030, there's 9 years away, you'll have 100% recycled content. So in summary, there is room for every scientist, every entrepreneur in the world. If you are on the waste management or circular economy, you could start looking at responsible use of plastics, enhancing recycling rates, innovative recycling technologies, or you could be part of the extended producer responsibility, which is a policy mandated by some other countries. You could also think of sustainable and green polymers, or designing polymers from the basics, from the molecules. You can actually redesign new kinds of polymers. And you could also look at new technologies like additive manufacturing. This conference is about direct digital manufacturing. Essentially, if it can reduce the carbon footprint of the products we make, that would be a huge contribution. Of course, you can leverage digital or industry 4.0 technologies like what I said about blockchaining plastics. Digital labeling is an important direction. So I'm a great believer that we, the humanity, benefited from linear economy, no doubt, for the last 150 years. That's why we have a high quality modern living. But that is not sustainable. Moving forward, we will have to move towards the circular economy. Good news is there are a lot more momentum in this direction now. So if I have to give a clear, short, crisp message, I like to say, for thousands of years, natural materials and more recently synthetic materials served the humans. Moving forward, they will be advanced, integrated as intelligent materials and systems, again for the benefit of humans. Moving forward, they will be harnessed further in humans' quest for low carbon materials, for low carbon economy and sustainable future development. With that, I think we will ensure we have a good life for the current generation. We also leave the planet Earth for the future generations in a better way. Thank you so much for your attention. As I said, even though I went very fast, all my slides are available for you. So you can send me an email directly, or you could approach the conference organizers. I'm more than happy to share slides with you. Thank you.
Thank you, sir. Any questions from the audience?
Yeah, Professor Madhav, I have one question to ask.
Yes.
Professor C. Raman, it was a wonderful lecture and I enjoyed it a lot. So can you hear me?
Yes.
So why do we need to make new plastics if recycled plastics can be reused?
Sorry, can you repeat the question?
So why do we need to make new plastics if recycling of a plastic can be done? Then why do
okay.
we?
Yes. Okay. Thank you for that question. I repeat again for the benefit of audience. The question is, why do we need to come up with the new plastics or new polymers when we already have existing ones and we can recycle them?
Yes, exactly.
There are two issues. Yeah. Yeah, there are two
Yeah.
issues. Existing polymers, there are lots of additives which we normally do not be aware of unless you are actually the manufacturer of the polymers. Most people use the plastics for the secondary processing. So these additives are added to enhance the processability and also the functional behavior. What happens is some of them are quite harmful. That's one. Second is as you are recycling, either mechanical recycling, chemical recycling, you are reducing the quality of the polymer chains. So because you are reducing the quality of polymer chains, recycled material will have a lower properties than the virgin materials.
Okay.
So that's an issue. That means how many times you can recycle is actually a challenge. And
Exactly.
not all polymers can be recycled very well. Right now, around the world, if you look at the big companies, they are able to demonstrate large-scale recycling for PET. But when you talk about other polymers, it's not so. So that's one reason. And second reason is no matter how many times you recycle, they are using, their first source is a petrochemical source. That means they are involved in extracting oil, coal, and gas, and they are involved with a higher carbon emissions, which are prone to be damaging the environment. Also, second one is these plastics, when they are left in the environment, they take hundreds of years to degrade. So
Exactly.
if you can come up with alternative materials, I think that's a good news. But if I want to give you another answer, it's a funny answer. That is only to keep all the young people here happy. Is they all need to get their PhDs. They need to do something new. So
Exactly.
it's a fantastic area to do research. If they do whatever they are done by their professors, their mentors, they cannot make a name for themselves. So let them work on alternative materials and they become more visible in their own way.
Thank you. Thank you. I have one more question.
Sure.
Whether this chemical recycling is good for sustainable development and environment? Chemical
Okay,
recycling.
so yeah. So the right now, answer depends on the life cycle assessment and boundary conditions. I'm just wanting to be more encouraging rather than discouraging to the people, because throwing away in landfills and burning is definitely a bad solution right now. If we start recycling, it may not be the best, I mean chemical recycling, but it's still better than pyrolysis, because the emissions are bad, or if left in the landfills is even much more damaging. So chemical recycling is better, but it's an energy intensive process. And there's also some kind of leakages in the process. They need to be fixed. And also there are at least 50 different chemical recycling methodologies. And it depends on how you can scale up, depending on your investments by the local governments as well as industry. So I think there is actually room for many players. Even though you might find a pioneer in one country, it does not mean that they can do recycling of everything. No. So I think that there's a good news for a lot of researchers and innovators and entrepreneurs. Yeah.
Thank you. Thank you, Sirama. Thanks a lot.
I think
From
Professor
Mitchell.
Pedrosa has a question.
Yes.
Yes, first of all, thank you, Professor Siren, for this great presentation and to share with all of us some of the results, but also some of the challenge that we have. In this pandemic context, with e-commerce, we as a society increased a lot the utilization of the uses of packages, and my question is I think is indirectly connected with your presentation, which is for you, which could be the main characteristics of the package of the future.
So a real last word. Can you?
Yeah.
Yeah.
If we think in a package of the future, which are the main, for you, the main characteristics that we need to have to try to design, to develop, to have research, to develop this kind of a package?
Okay, very good. I think, Rui, I think yeah, I can see that you will be a tough guy to answer, but I will answer. So one thing is we could go back to designing the product so that it's easy to recycle. Right now, many of the products are not made with recycling in mind. So that's easy, low-hanging fruit. We redesign products with the recyclability at the end of the life or at the end of the use. If that can be done, I think that's already a huge progress. Second one, those who are into the basic sciences, I would encourage them to redesigning polymer molecules. So they're designed to be easy to recycle. So that's another area. And the third one is if we can come up with less number of material combinations in any product, that would be ideal. Because again, when you are trying to do recycling, upcycling, one of the issues is segregation, separation. A lot of effort is gone into that. And that's where that comes in. So, and then if I had to go into the other, there's a lot of other interesting ideas where you actually do not package material or product, you provide the service. That means you actually think end to end, You are the material supplier, you are the product supplier, you are the service supplier in one umbrella, but you are responsible in collecting after the use. So that means the user is only thinking it as a service. If that can be achieved, my belief is we are going to change the whole industrial landscape. Yeah. Right now, these are all the ideas. Some of them being practiced by startup companies. But I think if we ask this question in 20 years from now, we will see many of those changes. Yeah. If you are looking at a simple, for example, how you choose to color the plastics or textiles is a huge opportunity to change them.
Marco, please. Yes.
Thank you very much.
Yes, thank you very much, Professor Siram. Fantastic presentation, and congratulations for the amazing breadth of work that you're developing in your laboratory. It's always a pleasure to watch your presentations. As you've shown us today, I think there is quite a lot of work being developed all around the world, and especially by industries in terms of this more sustainable economy around the use of plastics. I think my question is more, how can we academics and scientists, and obviously our industrial partners, actually do more to try to influence policymakers in order to make these more sustainable technologies widely available, but probably more importantly, how can we make these technologies affordable to the end users? Because I think that's probably what's going to trigger the use and the application of these technologies more broadly. Thank you.
Thank you, Marco, for the compliment as well as a question. And my answer is twofold. One is, if you look around all of us, when we did our PhDs, our university education, I think we did not have any subject on sustainability, right? So what that means is all the educators need to have at least one course. It doesn't mean they have to sit through the exam, but they need to be familiar with the major concepts. And until they are familiar with it, they won't be able to speak the language. So my suggestion is educators need to have a bit of a deeper exposure. Second one, policymakers are singing the song, but they're having a challenge how to pick the winners. So this is where the university professors have a huge advantage. Reason is they can mine the information and articulate well. And then they also have a master's, graduate student, PhD student, undergrad students, as well as others who are, especially the current generation, who are in their age of 20s to 30s. They're already kind of interested because it makes them look good. And say they would be interested in doing many projects, and curated information could be provided. But there are challenges. First thing is, especially materials and products, most of the data that is needed to show their environmental credibility, sustainability credentials, circularity, you need a lot of data. One issue is most companies treat that as confidential because it's their competitive advantage. So your biggest challenge is to get a curated quality information is the problem. So if that can be somehow university professors like you and me and all others can figure out, and then we will have a better way of articulating what are the choices would be better. So I think my view is this one. If someone is trying to build a career, as I said, there are two directions. One is you either make the materials intelligent or you make them sustainable. So either case will be fine. If you make them intelligent, that will be the future devices. And you make them low carbon, well, that's what the society wants too. So, and if you are smart and lucky, you do both the functionalities in same material, that's brilliant. So that means you have a material which is intelligent, is also low carbon. That's fantastic.
Absolutely, fully agree. Thank you very much.
Yes, Mitchell, sir. Yes, do you have any questions? Yes.
I have a question, but it's really a comment. I was just later in the I think in the poster session tomorrow evening, we have a poster which is about a project at the Polytechnic of Leiria, which is called Circular Seas. And this project is financed by the European Union through a particular Atlantic program. And the objective here is to utilize the waste that comes from maritime industries. So from fishing, from sports, and for beach occupancy and such things, and to collect this waste and to see how to upscale it by using additive manufacturing to make objects which will either be useful to the maritime industry or to the communities in which the waste is collected. And so we have ambitious projects to make some bus shelters, some bus stop shelters, and some urban furniture, as well as making some refrigerated boxes for fishermen to put fish in when they're collected to transport them back to the home. But it's an example of additive manufacturing adding to the circular economy and also upscaling it, because I think you're very right to emphasize the importance of upscaling, because at the moment in recycling there's a downscaling and it makes it very difficult for the recycling to be economically viable, because you can only make inferior products, and we don't need so many inferior products. What we need is a few, but much better products. And I would say to Professor Pedrosa, he might not remember, but we have a project which is about using natural polymers taken from the sea, from Mari, the Mari Research Center that Rui is based, it works in, and which is to coat this directly onto fish so that there is no packaging, but there is a preservative film to prolong the life of the fish. So I just give the two examples to show that the Center for Sustainability and Rapid Product Development is contributing in this particular area.
Thank you, Jeff. You made me jealous. No, it's good. It's really, really good, because the amount of plastic waste in oceans is a lot.
Yes.
And companies like Adidas already trying to collect these plastic waste from oceans, and they're trying to make shoes on demand. So my view is these are just a beginning. I think it's very good that you and your colleagues are actually already progressing in this direction. We're looking at a ways to collect them more efficiently, upcycling them. Yeah, I think that's the way to go, is because there's so much material out there. They have to be collected, because otherwise they're leading to microplastics, nanoplastics, and getting into the food chain. So obviously that waste have to be dealt with. So I think it's a really good direction.
Yes. So in the case of the fishing industry, bizarrely, the fishing industry is one of the major contributors to plastics in the ocean, because when they finished with nets, the simplest thing to do with the net is to cut the rope and let it sink.
That's right.
But there's tons and tons of nylon netting, which is just looking to be recycled, upcycled, and turned into productive products. And that's what the Circular Seas project is very much focused on.
Absolutely. Well, I think so. What you just said is there's a lot of work need to be done, and there's a lot more new minds, new thinking need to come in. Yeah.
So it is not question, Professor Sriram. It is answer to our conference chair, Dr. Ravindra Kamble. He asked, instead of inventing a new molecules, new polymers, let us use the same polymer, either composite or whatever means, he said. But I say, apart from using the existing polymers in different forms, there is an urgent need to even investigate a new polymers also, so as to give a new dimensions to the applications, For example, safe memory polymers, it can mimic the whatever we say, it mimics. So for which we need to investigate a new polymers. The existing polymers may not able to meet the requirement of the what to call applications of the safe memory polymers. For that, I think, still what I want to say is, apart from using the existing polymers, either recycling or any other means, so there is a need to even investigate the new polymers. I hope you agree with Sriram. You agree with me?
Well, I think what I totally agree with you. The reason is current polymers are fine, but the demand on polymers, functional requirements, is also enhancing.
Yes.
So, for example, imagine previously these phones were so big, but they're getting smaller, flexible, and requiring a lot of abilities to manage the heat and loads and things. And some of you might know, we are now using implantable devices that are put inside the brain and the human body. And human body has a variety of pH that can change from 5 to 9. So very aggressive, harsh environment where these devices have to function 10 years, 20 years, or even 50 years. So it requires also innovations and new polymers, because there is additional needs are there. So my view is both fronts have to happen.
Yes, I agree. So if there are no questions, I will conclude. Professor Sriram Ramakrishna, he gave a very good detailed discussions on the circularity and sustainability of the polymers. So you have nicely presented before the audience, though it is a online, but you have nicely presented. I hope it has reached all the audience. Some of our young colleagues may take up their future research in the sustainability and the circularity. With this, I thank the Professor Sriram on behalf of the organizing committee of ICDDMAP 2021. Thank you so much, sir. Danny Dewar is an architect with a strong computer science background. She obtained PhD in digital design and fabrication from Tishango University School of Architecture in 2019. And her research interest encompasses a variety of different topics, from robotics, artificial intelligence, material computations, to human-centric collaborative fabrication with VR, AR. It is her research vision to utilize emerging technology to enhance our ability to understand, design, and interact with the space, information, and material. She led independent workshops in multiple universities in China, with the topics ranging from customizing digital design interfaces, interactive design, AR, VR, robotic, to machine learning since 2014. As a practicing architect, she has worked for UN Studio during 2011 and 12, where she contributed on multiple competitions and commissioned projects. In the past, her design work have been featured in exhibitions such as Milan Triennial. She had been exhibition designer for exhibition in architect-centric New York and China Millennium Monument. She worked as the director of international collaboration for China Building Center since 2014, where the main responsibility is curating international competitions as well as education programs for institutions, developers, and government. So with brief introduction about Dan Leo, I welcome Dan Leo to give a presentation on large-scale additive manufacturing for construction. Thank you, Dan Leo. Please give a talk.
Thank you, Professor Jeffrey. It's a pleasure to be invited here. So I'm just going to quickly share my screen. One moment. Can you guys see this?
Yes,
Hi.
yes, yes.
Yes, perfect. So the topic of my talk today is about small to large towards the large scale additive manufacturing for construction.
Then I'm sorry, we're
Yes.
seeing a window from your Zoom application in front of the PowerPoint.
One moment.
Where you
this
choose
okay?
your background, maybe.
One moment. Okay, let me reshare my screen. Just a second. Share screen. Is this better?
Yes, no, it's okay. Sorry. Go
No
on.
worries. Thank you. So the topic of my talk is to negotiate between the scales and trying to study how the additive manufacturing process could be scaled up and be applied in construction settings. So my name is Dan Lo. I'm a current lecturer in University of Queensland in Australia. So my talk will quickly be going through a few different projects. So we started with some projects that are expanding the current system of additive manufacturing, and I will move on to some demonstration processes that are based on architecture practice and my current ongoing research to explore a synthetic approach between additive manufacture and material and structure innovations. So this is one of my earlier projects. So we get to know about of course, 3D printing, the typical FDM process, back all the way in like almost a decade ago. So, but however, as architects, it is almost impossible to apply those kind of small scale prototyping system in large scale settings. So some of the earlier studies is talking about how to scale up and increase the fabrication speed with a combination of the additive manufacture process and innovative inspirations from structure systems. So this is one of the earlier examples that we are working about the strategy of 3D printing. It's basically retrofitting a 3D printing and effector to an industrial robot. And this is actually a reference project, a mesh mode by Norman Heck and from Etihad. So as an extension from this project, and we're looking for a more dynamic approach where they're able to generate fabrication sequence and calculate the path planning, as well as to do the structure validation for each interim step of the spatial wireframe extrusion. So instead of working with a more uniform, optimized mesh structure, the goal of this research is to print a generic spatial mesh. And there are a few challenges in this process in terms of the path planning. First one is a sequence finding, and the challenge is that we have to make sure that it minimizes the spatial deformation at each interim rim step. And the second one is that we have to avoid collision of the later collision that may cause for the working range of the later steps. So I'm just going to go through this project quickly because this is one of the earlier project. One of the configuration and the mesh optimization involve around the configuration in coordinates with the logic of the robotic arm, which means that the end effector needs to be minimized in terms of the volume, and the orientation and the collision area of the end effector need to be considered to evaluate if the mesh is actually printable or can be optimized. And such orientation of the each, so it's different from the typical FDM method. In this case, the orientation of the each struts needs to be considered during the path planning of the robotic fabrication. And also because this is an iterative process, and we have to, so we did a few optimization method to reduce the calculation speed and break the larger mesh into the smaller segments. Some algorithm for decomposition as well. So this is the overall workflow and idea behind this earlier prototype about how to use the current 3D printing mechanism to print a larger spatial structure in a more material and time effective method in coordination with robotic automation. And this is one of the comparison between the simulation and our final extruding process. And this is our overall fabrication sequence. So, but however, the one issue about in this case is that the algorithm is extremely time and computational power consuming. So it takes about 8 to 10 hours to optimize for a very simple mesh, so that we have to ensure the mesh itself is valid, and we have to ensure the sequence and the printing process can be calculated and is achievable together with synchronized structure calculations through each iterations. And based on this one, there came to one of my later projects that are about using 3D printing to dissociation the path planning, so and the printed outcome. Because one of the major collision we noticed in the earlier prototype is that because there is a high demand for the working range of the robotic arm, so there are a lot of effort to deal with the collision-free extruding process. So we're using image capture and AI to find a way to disassociate the path planning with the printed outcome, so that the end effector essentially move in 1D, while the printed outcome will achieve the target form with a natural deformation and curing process. So this is one of the more exploratory project that works with robotic automation, image recognition, and machine learning. And so we're also utilizing the automation power of industrial robot arm to build this automatically testing platform that can collect the image and analyze the data at the same time. And we did a very brutal one-to-one mapping between the printed outcome and the control parameters. So this is the outcome of our trained forward model and the background model. So the forward model basically means we know what is a G code, but what would be the printed outcome. While the backward model is that we have our printed outcome, then what is the G code? And here are some samples of the printed outcome. That is a little bit of background to research that on how we're trying to scale up with the typical 3D printing method. But as I'm a practicing architect from architecture school, so we constantly confront with this kind of industry demands that they don't want to wait for all the time to scale up the current system, and they just want to be offered with applicable solutions. So the next two projects is based on my architecture practice and a collaboration with my professors and my colleague to explore how that additive manufacturing process could be applied in construction industry. The first one is what we call slip form casting. It is kind of the alternate form of the additive manufacture. So it starts from this kind of architecture project. So we're commissioned with this building where each of the louver is rotating in different angles according to environmental and solar exposure, solar angle calculations. So we're confronting that either we create like 2,000 different modes for that each of these prototype, each of the louvers, or we use alternative additive manufacture process that we can accommodate the complexity in geometries without the significant increase in cost. One inspiration is from dynamic slipform casting, also from the Grand Mazio Cooler Research Group in Etihad, where it's a migration between the typical casting process, slipform casting process, and additive process, so that the concrete is being poured, cured, and the pressure to deform with this elasticity deformation at each individual steps of the extrusion. So based on this inspiration, we developed our own system that would accommodate the commercial application, especially for this project. Because one challenge is that we need to reduce the material cost, we need to add the reinforcement, and we need to increase the extrusion speed comparing to the prototype that are more developed in the lab settings. So different from the original process of the highly customized concrete being poured during the extrusion process, we had the alternative process where we were using a uniform stainless steel mold and have the bulk concrete cured altogether, and it deforms the concrete while being extruded from the mold and being rotated. So this is so the benefit of this process is that we can significantly reduce the curing time of the concrete. So basically they're pre-cured to the right moment, and they can be extruded in this more pipeline method. Here, I'm not sure if you can hear the video. Can you guys hear the music? Just wondering. And this is the final outcome of that fabrication process. So the second more industry-based project is also in hybrid between the typical additive manufacture process and the construction process. So there are, when we talk about bricklaying, there are quite a lot of work on assemblies and the brickwork. And based on that, we will start to look what would be the bridge between the lab environment. And so this project is actually in rural China, so it is not like in our ideal lab environment, and the budget, it does not allow us to afford customized, highly accurate bricks and the structure mortars. So that we're dealing with the low quality vernacular non-facing brick, and for the bonding, we're staying with a normal traditional thick bed of cement mortar base. And the way you were thinking about of creating a dual-purpose end effector like mechanical system that could both accurately place the brake as well as print the motor at the specific place of the overlapping. The end effector itself is quite simple. So basically composed of a calibrator and composed of the concrete printer and composed of a pneumatic vacuum lifter for the picking up the brakes. It is straightforward system design that allow us to calibrate the height for each individual pass at the end of the cycle, at the end of each layer. Here are some prototype and some very rough structure experiments. I think those are two very interesting exploration by combining the advanced manufacture process like robotics and industrial robots and automations with construction projects. It raises a question about the what kind of fabrication method that are actually suitable in the construction settings, because of course there are a lot of explorations on let's say concrete printing and etc. for those kind of large scale projects, especially in labs and in research labs. But it's just that in our practical experiments that we noticed that some of the common challenge are the restriction of the fabrication time, and as well as how that system could actually fit into the current structure system and construction process, and how the requirement about the cost limitations for customized materials. So those are some of the main challenges that I noticed during my practice in architecture and applying those kind of novel technologies. So that actually leads to my last project I'm going to show, which is something that I'm currently working on, that are actually confronting those concerns. So the last project that I'm going to present more in detail is the robotic weaving of the customizable FRP framework for large-scale optimized structure. So this is one of my ongoing research. So unlike the previous ones, we haven't achieved the end products, which is like a constructed full-scale prototype, but a lot of the ideas are already calibrated in the current progress. So the idea comes from that instead of using current concrete printing as our default material for large-scale additive process, we thought we were inspired to think if we could use this kind of fiber reinforced polymer, which is a common material that they use for structural reinforcement, and combine with robotic fabrications to create this kind of novel additive process that are suitable for large-scale structures. So we also used the KUKA robotic arm as our default mechanism to develop our prototype onto. The goal is that to create an additive system that can accommodate the geometrical freedom in terms of variation in sections and the directions. So this is where the idea of these projects come from. So unlike those kind of concrete printing and a lot of the large-scale printing, like with the forms and etc. So a lot of the current research in large-scale fabrication come from the material research. However, our topic research actually come from an established material structure system and the construction system, which is use a hybrid double skin tubular, this kind of tubular form for structure confinement and for casting. So the formwork is an in situ formwork that both serve as structural reinforcement as well as the formwork. And just looking at this, we will start to wonder if we could actually create a novel fabrication system based on this. So the benefit is that it obviously can be accommodated into the current construction process. It has a very specific application outlook, and it has proved to be both excel in terms of the structural performance as well as sustainable like industry supply. So the idea is that we're using in the current system, they're using the FRP formwork as a structural confinement reinforcement and the casting place formwork. So in our research, first of all, the challenge is that of course, the typical path planning, which is different from the typical FDM methods, it is essentially a winding process. And as a formwork needs to be, will act as an in situ reinforcement after the concrete testing. So unlike like my previous research where the component just need to be self-structurally sustainable, this component actually serve as a research structure purpose that need to be further evaluated. And for the on-site fabrication, there are limitations in material transportation and selection. Though it is an ongoing research, so I'm only showing this is the first prototype. So the first prototype is quite simple. So there is a 2 roller and a FRP roll at the back. And there is a middle part, number D here, represents a system to apply the fast cure epoxy resin. So the epoxy resin will be cured while the system is weaving the fabric into form. So could be better represented, but this is the intent. This is essentially the fabrication process for during extrusion. Of course, different from the current FDM printing method. So this, so in this kind of fabrication with fiber reinforced polymers, the support and the system relies on the cross-lamination between the layers. So it is essential to ensure that the fabric, when it's cured correctly, so that itself is sustainable and the right amount of the pressure, it's up and speed is coordinated so that each layer is laminated correctly, because the cross-lamination and the tightness of the system directly relates to the latter structural performance in terms of reinforcement. Also, there is a trade-off between the layers and the fabrication speed. So of course, the more layers, the more solid the system is, but it does requires like it multiplies the fabrication time. Of course, and another topic is about the calibration of the resin, because the viscosity of the resin that we want the resin to not 100% permeate the system, so that it will still have a more or less dry surface in the inward side that allow the roller to perform smoothly. And some of the main parameters that we calibrate, of course, is the total height and geometry, is the space between the layers, and the distance of overlapping between layers in correlation with the different epoxies and different curing time during speed. So this is the time lapse of the fabrication process. And we also test different FRP layers. And so this is an experiment with different trials of failure and success. So we have found that about, just based on experiment, between 15 layers and 20 layers is like the minimum amount of the layers to support the system, actually just based on the epoxy resins that we're currently using. The system is scanned to evaluate the accuracy of our first prototype. So this is our first prototype, and we have learned a lot about what to improve from now on. So it's a range of combination between the selection of the resin and the way the roller mechanism works. So that's a first prototype, but we did have a few new prototypes that we just did last month that are about 1.5 meters tall. But just through this, because this is ongoing research, so through these experiments, we did identify a few problems that includes the delamination between the system, as well as the restriction of the curing time, so that fabrication speed could be significantly increased if we increase the curing speed of the epoxy, but that brings another layer of the challenge for the control mechanism of the application. Of course, as architects, so the project always relates to a grander vision about the project of what can be done can this system be useful in architecture? So this one actually developed the innovation for the optimized structural system. So this is one of my collaborators' research on the topological optimized structure. So the restriction for this system is that even though they're able to develop the highly efficient system, but the fabrication costs and time for those can be irregular components greatly offsets the optimization in terms of the material efficiency and etc. in the optimization process. So there is a trade-off between the more optimized the geometry is, then the more expensive it is going to be fabricated with the traditional approach. So we have worked together to envision how that the fabrication system we developed could be applied in this scenario. So this is just one case study about how the system could be applied in the joint into an existing structure system. So, and so this is a prototype we're working on, so it is not fully developed, but another idea is that because the structure performance and the lightweight of the FRP tube allows this process to actually be performed sideways, which would greatly expand the building envelope of the system, because essentially we can put the robotic arms on a rail that extends the fabrication workplace. Of course, so with our current prototype, we're evaluating its structure performance in thermal reinforcement and comparing that to the typical fiber polymer FRP confined reinforcement in tubular structures. So that is about the background of my work. I believe I'm only given a 30-minute slot to presentation. So feel free to ask any questions.
Questions from the audience?
Yeah.
Mitchell, sir, yes.
Yes. Yes. Thank you very much for the excellent presentation, Dan. Could you just say when the topological optimization is performed, does this take into account the complexity of the manufacturing process, or is this as in a topological optimization just minimizing the mass of material that's used?
So the reason why it's the BISO system like this kind of topological structure optimization system is difficult to be applied in architecture and this kind of large scale construction is that it is purely structure and optimization process. It does not take into the complexity of the fabrication. So the outcomes are often used in aerospace where the components where the fabrication cost is not a main concern and where the components are relatively small, but it's just not applicable in current method of how we build buildings.
Okay, thank you.
Questions? Any questions? So if there are no questions, I thank Daniel Liu for giving a detailed account on the different approaches employed for the construction of buildings, including a direct digital manufacturing. Thank you so much, Daniel, for agreeing to give a talk on what you call large-scale additive manufacturing for the construction and giving the lecture. Thank you so much. Thank you so much.
Thank you so much. It's an honor to be here.
And next speaker, shall I call Mitchell? Shall I call the next speaker?
Yeah, sure, yes.
Dr. Marco is here. Yeah, I hope. Yeah.
Yes, I am.
Yeah, I welcome Marco to this conference. Dr. Marco Dominguez is a senior lecturer in the Department of Mechanical, Aerospace and Civil Engineering at the University of Manchester, UK. He graduated in Mechanical Engineering from the Polytechnic Institute of Leiria. He is alumni of IPL, and hold PhD in 2013 in mechanical engineering from the University of Girona, Spain. Before joining the University of Manchester, he worked for 2 years as assistant researcher in additive manufacturing at the CDRSP in the field of CDRSP Portugal. He is a principal investigator at the Henry Rice Institute, Manchester, where his group develops advanced biomaterials and biofabrication strategies for application in tissue engineering and regenerative medicine. He holds several visiting professional positions at prestigious institutions, including the Institute of Composite and Biomedical Materials, University of Naples, Italy, the Center for Rapid and Sustainable Product Development, CDRSP, and the Center for Reverse Engineering and Additive Manufacturing Innovations, Department of Industrial Engineering of the University of Naples, Italy. He authored more than 50 publications in international journals, books and book chapters, and holds 2 international patents. Under his guidance, 4 students obtained PhD. With this brief introduction, I once again welcome Dr. Marco to give a presentation on bioprinting strategies for regenerative medicines and disease modeling applications. Marco, yes, you can start now.
So I'm just sharing my screen. Can you see my screen?
Yes.
Okay.
Okay, brilliant. Thank you very much for your very kind introduction. Before I start, I'd just like to take this opportunity to congratulate the CDRSP team and the Karnataka University for the organization of this fantastic event. And especially I'd like to thank Professor Nuno Alves and Professor Geoffrey Mitchell for this very kind of invitation. It is indeed an honor for me and a pleasure to be here and have the opportunity to share some of the work that we are doing in Manchester in terms of biofabrication for healthcare engineering. And as an alumni of the Polytechnic Institute of Leiria, and also as a former member of the CDRSP, it's a special feeling to have the opportunity to come back to this place that I also call my home. Even though just remotely, it's always a pleasure. Finally, just a word to all our friends and colleagues in India who are suffering tremendously from this pandemic situation. I'm sure that all our thoughts and hearts are with you in this very difficult moment, and we all pray that you can come out of this situation very soon and return to some sort of normality as well. So I apologize in advance because I've got a few extra slides, so I'm going to try to keep everything within the allocated time that was given to me. And over the next 30 minutes or so, I'll try to give you an overview about the work that we are conducting in our research group in Manchester in terms of biofabrication strategies, both for organogenesis, but also in terms of disease modeling. And I'll try to showcase that with some case studies that we are currently working on. So for those of you who don't know, Manchester is located in the northwest of the UK. As we were discussing before starting this conference, Manchester is well known for its nice, warm, sunny weather, but also Manchester is quite well known for its football clubs, Man United and Man City, and for its strong musical culture. Very famous bands like Joy Division, Oasis and James were actually born and started in the UK. But Manchester is also the home for the University of Manchester. It's one of the oldest universities in the UK, actually the largest single campus in the UK with over 40,000 students. and also one of the most important universities in the UK, but also in Europe and in the world. Since 2020, Manchester is also the home for the Henry Royce Institute. And I think, like Professor Ramakrishnan was mentioning before, we came to a point that it's extremely important that we develop at academia new strategies to actually transform our society into a much more sustainable place for all of us to live in. And the Henry Royce Institute's vision of advanced materials is actually a vision to transform our society into a much more sustainable one. And this is enabled through a UK-wide network of academic champions trying to develop technology to address global challenges. And there are multiple challenges, ranging from biomedical devices through plastic sustainability to energy efficient devices, supporting key national targets such as our recently established zero carbon targets for 2050. It's an investment of around £315 million. The hub, like I said, it's in Manchester, but we have partners across the UK in Oxford, Sheffield, Leeds, and many others. This establishment of these institutes makes part of a broader strategy also of the UK government that recently has defined the 8 great technologies where the UK is set to be a global leader. And one of those areas or great technologies is regenerative medicine. And our group in Manchester is very much focused on the development and the application of biofabrication technologies to develop models that will allow us to investigate mechanisms associated with regeneration of tissues, organogenesis, but also on models that will allow us to understand mechanisms associated with different types of disease. And I will talk about some of those throughout this presentation. I guess if you type bioprinting on Google, probably one of the first images that you will come across is actually this one. This is Anthony Athala during one of his TED Talks in the United States. Anthony is probably considered the pioneer of bioprinting. And what it's showing in this slide is actually what resembles a kidney. Obviously, it's not a functional organ, but it gives a very good idea of what can we achieve with this bioprinting technology. And this was probably one of the very first attempts to try to develop artificial organs to tackle this world problem that we have in terms of organ shortage for transplantation. But I guess that the quest for regeneration of human body is not something new, and obviously it didn't start with Anthony and his pioneering work at the Wake Forest University. And we can find references to regeneration in ancient history. So I'm sure that you're all familiar with the myth of Prometheus, and this was probably the first reference to tissue regeneration that we can trace back to the Greek mythology. He was actually punished by Zeus because he stole the fire from the Olympus and gave it to men. Obviously, Zeus was not happy with it and decided to punish him. He decided to chain him to a rock, and every day an eagle would come and would eat his liver. This would then regenerate, and the eagle would eat the liver again. And this would go on for eternity. Obviously, we as humans, we do not have this capacity, and our regeneration ability is actually very limited. However, we can find examples of regeneration capacity in nature and all around us. And in this short video, you can see this amazing creature, the salamander. This is actually a fantastic creature that is capable of fully regenerate an entire limb, including both soft and hard tissues, in a fully orchestrated manner. So if you chop a limb of the salamander, she will start or trigger this regeneration process by recruiting cells from the adjacent tissues. And in a very articulated process, it's able to fully regenerate these soft and hard tissues and reconstruct the limb again. But again, we as humans, we do not have this capacity, and we need to develop tools to actually be able to stimulate, support, and guide the regeneration of our damaged body parts in a very similar way to what the salamander is capable of doing. And that's where bioprinting becomes important in terms of tissue engineering and regenerative medicine. I guess that in very simple terms, bioprinting is nothing more than just a group of computer automated techniques that allow us to transform a digital model or design into a 3D physical model through a layer by layer process where we can combine different cells from human patients with biomaterials to create artificial tissues and organs for transplantation. As we have also the possibility of combining these technologies with imaging technologies, we can go a step further and develop personalized therapies that can be customized to specific defects, but also according to the specific genetic composition of each patient. And there are, I guess, different approaches that we can follow in terms of bioprinting. They can be generally divided into top-down and bottom-up. Top-down approaches normally require the prefabrication of a physical template that we normally call a scaffold. This can then be combined in vitro with cells from the patient, different biomolecules, can be cultured in vitro to allow some pre-maturation of the tissue, and then implanted back into the defect site. On a much more biomimetic approach, called also the bottom-up approach, we can follow a similar process to what our cells do in the body. So if we combine or if we use the cells as building blocks, we can assemble them into modular constructs and then into much more hierarchically organized constructs that can resemble tissues and organ functions. And I will try to give you a few examples how we are using these technologies independently or in combination for the creation of tissue surrogates. So I guess that top-down approaches are particularly well suited for a skeletal regeneration. And in the next slides, I'll try to show you some of our initial work on the development of bioprinted constructs for bone regeneration. And this started a long time ago, back at the Center for Rapid and Sustainable Product Development, if I'm not mistaken, back in 2008 or 2009, with a very small group of people. Obviously, things have evolved greatly since then, but at that time, this small team of researchers developed the first, or one of the first, multi-material bioprinting systems capable of printing constructs using different types of polymeric materials or composite materials, but also with the ability of incorporating for the first time cells in the printing process. And this was the first technology called the bioextruder. And just to mention, I think this is a very good example of what the center has been doing over the life of this institute. This technology, developed back in 2009, was then adopted by a Swiss company called RegenU. And RegenU now commercializes this technology under the brands 3D Discovery. And RegenU is actually one of the leaders nowadays in terms of bioprinting technology in the world. So a very good example how technology developed in scientific institutions can then be effectively translated into the industry with huge economical and social impacts. as I was saying before, I think one of the main focus at the time was the development of 3D scaffolds for bone regeneration. This is actually an example of a work that was developed in collaboration with the Queensland University of Technology and Professor Dietmar Utmaka. What you can see here is a cellular construct, a scaffold. It's a composite material made of polycarbonate with tricalcium phosphate. This was used in a tibial defect in a sheep model to try and understand how could we use this material and optimize, obviously, the architecture and the dimensions of these constructs to promote the guided regeneration of large bone defects. And some of our initial work and interest at the center at the time was very much on what was the effect of the internal architecture of these constructs on the mechanical properties, and how could you use those parameters to tune the mechanical properties and match them with different types of tissues. So our initial work was very much on building scaffolds with different pore geometries and dimensions, and understand how that affected the mechanical properties of the scaffolds. And what we've realized is that by controlling the pore size, we could control the mechanical properties under compression for skeletal regenerations. But also, and probably more importantly, we understood that for a broad range of cell lines, we could control also the function of these cells. So by changing or by using different pore architectures and dimensions, we could control the differentiation, in this case, the osteogenic differentiation of mesenchymal stem cells, but this was applied to a wide range of cells. And what this has allowed us at the time was to build a database with information that we could then use to develop tools for the automated design of scaffolds for tissue engineering. And I think this is something that the center has been very strongly developing, these automated tools for integration with computer-aided design and with bioprinting that will further support and enhance the translation of these technologies into a more clinical set environment. Since then, and probably this, since I've joined the University of Manchester, we've been focusing a bit more on bottom-up approaches. And basically because it's, as I was saying before, it's a much more biomimetic process that replicates more closely what happens in the human body. And in general, this requires a combined use of cells, biomaterials, mostly hydrogels, as biowings. And the example that I brought you today is of a project that we have in collaboration with different clinicians in Manchester. The idea of this project was to develop these 3D humanized models of human brain to try and decode the mechanisms associated with the initiation and the progression of dementia. The reason why we've started this project was basically because there is a huge lack of proper animal models that will allow us to study the disease, and also because it's very, very difficult to access the human brain. And in this case, as you can see here on the left image, this is a healthy neurovascular unit composed with small blood vessels, neurons, astrocytes, pericytes. So there is a large number of cells, a very complex structure that is quite difficult to replicate. And what happens in disease initially is that we have a disruption of the blood-brain barrier. So the tight junctions that maintain the endothelial cells together and that prevent toxic substances to enter the brain and to disrupt this neurocoupling between the different cells that compose the neurovascular unit is disrupted. However, we do not understand exactly the mechanisms that lead to the break of these tight junctions and the development of the disease. In this project in particular, we are interested in understanding how the accumulation of amyloid beta lead to the disruption of these tight junctions. So for that, we've developed a protocol where we use iPSC cells, and then using small molecules and different growth factors, we can differentiate them into the different cells that we have in the neurovascular unit: neurons, astrocytes, pericytes, etc. But then we need to organize them, or to position them in 3D in a way that can also resemble the native organization of the cells in the human brain. Obviously, using hydrogels, it's quite complicated to obtain this precise spatial positioning of the cells. So in order to try and tackle that problem, Sam, who's one of our postdocs, developed a process of additive manufacturing called SLAM, suspended layer additive manufacturing. And what this process allows us is to print hydrogels with very low viscosity, and also with very low stiffness, which allows us to mimic the properties of the brain, and allows us also to do that with very high shape fidelity. How can we achieve this? So we have normally a bath containing agarose, which is a fluid gel, and this bath works as a supporting system, where we can then print inside different bioinks without any cross-linking. And after the positioning of these bioinks, we can then cross-linking using ionic cross-linking or UV cross-linking, depending on the materials that we are using. We can culture them inside this suspended bath, or if we need to do any further analysis, we can just wash away the agarose and obtain our three-dimensional construct. So this system actually allows us to overcome the limitations in terms of the printing of low viscosity materials with very high shape fidelity. Our work initially was very much focused on developing cell-laden hydrogels for the in vitro culture of functional neurons. So we started working with alginates and collagen. We're able to tune the mechanical properties and the rheological properties of the system to allow for the encapsulation of the iPSC cells, and also to allow us to actually print this in a fully automated manner. And this is what you can see here. These are directly printed into the tissue culture plates. They maintain their shape and dimensions. And after printing them, we were able to actually validate the process by evaluating the function of the neurons. So these are functional neurons, as you can see here, fully mature. And this was the initial work developed by Sam. What we are now doing is incorporating the other cells that we have in the neurovascular units, increasing the complexity of our model so that we have a much more physiologically relevant system to actually study the development of the disease. Unfortunately, I don't have the time to go into detail about this, but I'm happy to provide any further information if that's of interest to you. In terms of hybrid approaches, or in other words, the combination of top-down and bottom-up, these are particularly relevant when we want to create constructs or scaffolds capable of providing both mechanical support, but also an ECM-like environment to the encapsulated cells. This normally requires the use of multiple materials, normally cell-laden hydrogels in combination with thermoplastics or composite materials to ensure the good mechanical support. The example I brought you today is related with articular cartilage. This is something that we work or that we focus quite a lot in our group, and shows how we can combine bioprinting with biomaterials and stem cell technology to develop mechanically stable cartilage implants. As you probably know, osteoarthritis is a major health problem affecting the mobility of millions of people worldwide, and it doesn't have an effective therapy available at a clinical level. It's normally characterized by a gradual degradation of the articular cartilage, and depending on the severity of the lesion, it can progress towards the subchondral bone, at which point a full prosthetic device is needed to restore patients' mobility. So our strategy is actually to try to restore the full function of cartilage in the long term and try to transform this disease tissue into a fully healthy tissue. So it's not just repair, it's full regeneration. And there are different challenges. One obviously is the ability to generate and maintain the articular cartilage tissue in the long term. Also, cartilage is organized in different zones with different mechanical properties, different functional properties. So our ability to replicate this tissue heterogeneity is quite limited at the moment. And another challenge is obviously to restore the physical integrity of the tissue so that it can withstand both compression and shear forces in vivo. This is a work that did not start in Manchester. It actually started back in 2012 through a large European project that the CDRSP was involved with partners across the world called Hydrozones. But the way that we're doing, or that we are addressing the problem now, is by trying to decouple the ECM environment requirements from the load-bearing properties. So what Miguel, one of our PhD students, is doing first is developing a chondrogenic hydrogel capable of supporting the encapsulation of human pluripotent stem cells, but also their differentiation into chondrocytes. He's working with different types of materials. One of the materials is based on alginate, but we're also working with other polymeric materials, trying to understand which is the best material that supports the function of pluripotent stem cells. And this will provide the ECM-like environments required by the cells, but in parallel is also developing in collaboration with the University of Coimbra, new polyester urea materials that have much more suitable mechanical properties for cartilage from a viscoelastic point of view, and then combine these two systems into a hybrid construct that will provide the ECM environments required for the cells, but also the mechanical properties or the mechanical resistance that is required for the cartilage to function properly. From a biological point of view, I'm not going to go again in detail about the differentiation process of these cells, but our aim is actually to recapitulate the human limb development from the initial inner cell mass to the primitive streak following the lateral plate mesoderm pathway in order to obtain higher limb cartilage. For that purpose, Miguel is using a protocol that was established at the group of Sue Kimber, who is one of our collaborators, through which you can generate chondroprogenitors from human pluripotent stem cells simply by the modulation of Wnt and retinoic acid signaling. And obviously this requires a time-dependent use of small molecules and growth factors like CHIA59, TTNPB and BMP2. And as I said, I don't have the time to go through the detailed protocol, but if you want to know more about this, you can find in a recent publication. It's in bioarchives, but I'm also happy to provide you more information about this. So the first step is actually the generation of these chondroprogenitors in 2D. This is a protocol that requires 11 days. Then what Miguel does is to create cell aggregates using these microells, and after a day in these microells, we encapsulate them in the gels. And what we can see when we encapsulate them in the gels is that in general, we have a very high cell viability. So cells are kept alive, even though we have aggregates. The addition of the collagens normally leads to a migration of the cells out of the aggregates and the colonization of the gels. But I think that more importantly is that the combination of these cells and the aggregates actually enhance the expression of chondrogenic markers like COL2 and SOX5 and SOX9. And importantly, also reduces the expression of collagen 1, which normally we don't want. Also, in terms of markers, and importantly, it's we have, through this protocol and the combination with these gels, we have a very low expression of pre-hypertrophy marker runs too. What we are doing now with this is to actually run long-term in vitro cultures before we start implanting these aggregates in animal models, in horse models, in collaboration with the University of São Paulo in Brazil through a project that we have financed through the FAPESP. In terms of the more mechanically resistant constructs, and as I've said before, in collaboration with the University of Coimbra, with Professor Jorge Coelho, we have developed this polyester urea. We've compared the performance of these materials against polycaprolactone, which is a very commonly used material in terms of bone tissue regeneration. And we did that by looking at cell viability and metabolic activity after 21 days of in vitro culture, but also in terms of gene expression using real-time PCR, looking at specific markers like COL2, aggrecan, and SOX9. And what we've realized is that when compared to PCL, we have a much softer matrix that actually allows us to get cells with a morphology that it's much more mimetic of what we normally find in chondrocytes in native cartilage, but also we have an improved or enhanced expression of aggrecan and collagen 2 essential markers in chondrogenesis. What Miguel now is doing together with Fabrizio is combining this cartilage protocol and materials with a protocol for osteogenesis, or in other words, for bone, and trying to develop a fully organized osteochondral model containing both the cartilage part and the chondral part fully integrated. So I guess the question is, what lies ahead in terms of bioprinting? And is what we normally see, or what we see in Westworld and science fiction series, is that going to become a reality? Is that just a distant future, or maybe just something inevitable that we'll all have to face in the near future? I guess we're still a bit far off from that. I guess we're still a bit far off from being able to actually print fully functional organs. I guess there are many challenges that we still need to address before we actually achieve that, from vascularization, not just the creation of vascular channels in vitro, but also how we then incorporate those vascular channels and integrate them with the native vascularization in the tissues. We need more materials, but I think from a manufacturing point of view, there are significant challenges. The scaling up of the 3D printing technologies that will allow us to print implants or surrogates that have dimensions relevant for clinical application, but also how we scale up the manufacturing of materials, how we scale up the manufacturing of cells to incorporate with these tissue surrogates. But I guess the word somehow is convergence, and there are opportunities that we can all explore. I think the integration of bioprinting with stem cell technology is probably one of the most important ones. And this will take us a step forward to this objective that we all have, that is the development of personalized therapies. We can use iPSC cells to actually be able to develop implants, therapies, medicines that are actually customized to each patient, that are personalized from a genetic point of view. And this will be a step forward in terms of personalized medicine that will need to be available to everyone, but also at affordable costs, not just for the rich ones. And I think this brings me to the end of my talk. I'd just like to thank all our collaborators, obviously our group in Manchester, the students that actually do the work, but also, of course, all the academic collaborations in Manchester and across the world, and in particular, thank you all for listening to my presentation today. If you've got any questions, I'm more than happy to answer them.
Any questions? Questions from the audience? Yeah, please, Mitchell, sir.
Yes. Marco, excellent presentation. Thank you very much for all of the details. I suppose as a potential recipient of some of these therapies, maybe more than you, I have an interest in the timescale, and I just wonder whether, because other people have commented, I believe there was a report in the European Union which was to say that regenerative medicine had promised a lot but delivered very little. I don't mean scientists had delivered, but as a therapy had delivered very little. And I just wonder whether there's a basic principle that's been missed in the process, because you speak as if all of the ideas are there, and I think one of the most challenging ideas is that you're talking about elaborating the extracellular matrix, but in actual fact, I'm always struck by there's a tissue culture matrix that's produced in the UK that goes under the trade name Alvatech, which is a very simplistic polystyrene, porous polystyrene matrix, and tissue grows on this perfectly well. And so I'm not saying it grows in a way that can be made to generate a replacement tissue, but it grows. And so whether the complexities of the extracellular matrix aren't really being reproduced sufficiently well, as you pointed out with the new material you're working with from Coimbra, etc. I just wonder whether you think there's a possibility that there's a basic principle that's been missed, or that's missing from it, not through any problems of the work, but more just the way that the concepts are being constructed. Because it seems to me there's a blockage in this in the system for turning these therapies from what is a reasonably well articulated concept into a clinical reality.
No, absolutely, Jeff, and thank you very much for the question. I think that's very relevant, and I fully agree with you. If we step back probably 10, 15 years, a lot of people said that 2010 would probably be the decade of organ printing and bioprinting in general, and we'd all be going to the hospitals nowadays and get a tissue replacement. I think that was a bit optimistic. And I think we have, some responsibilities in that. I think we've created an idea that 3D printing and bioprinting in general would solve all of the problems in terms of, alternative therapies. And we did that without having without being fully aware of the challenges that we still have in trying to understand very basic mechanisms related with tissue regeneration and mechanotransduction. How is that actually used by cells to create matrix to regenerate tissues? We still don't understand that. We're still in the very early stages of that. And I fully agree with you. And I think the question is, do we need to actually create very complex ECM-like environments to actually, be able to regenerate tissues that are functional in the future? I don't think we do. I think what we need to do is to create materials that will provide a support for cells to function, but then most of the work needs to be done by the cells. And I think we've been missing that for a very long time. And we are just now realizing how developing simple materials, simple chemistries with simple structures can be effectively used to support the cells in initial stages of development that they will then be able to use to create much more complex structures through the deposition, orchestrated deposition of extracellular matrix that will then be assembled into much more complex tissues. I think you're absolutely right. And I think we need to take a step back and look at this in a much more simple and straightforward manner. I think the other blockage, Jeff, is that we haven't been able, like Professor Ramakrishna was mentioning before, we haven't been able to standardize most of the methods that we use to culture cells, simple things from extracting cells, creating bank cells, and also the materials that we produce and the technologies that are used to then bioprint these constructs. So I think we need standards, and we all have a role to play in that. But I also think that organizations like the FDA, the European Agency, have a role to play also in the regulation of bioprinted products. We don't have that. And until we don't know the rules by we need to play, we won't be able in our small labs to actually develop things that in the long term will meet all those requirements. So I think we need, and I think that's why these conferences are extremely important, because I think we need to come together and to actually define a very clear, robust roadmap to actually be able to translate these technologies in the future and stop making false promises that are never delivered in the future.
Thank you very much.
Anybody wants to ask question?
Yeah, may I?
No, yeah.
Okay, thank you. Good morning to everybody, and congratulations, Marco. Congratulations for your inspiring presentation. It is very, very relevant, and it is always a pleasure to me and to, I think, to everybody from at CDRSP, and I'd like to congratulate you for your position in a very important university around the world. It is always a great pleasure to see more young people to have these relevant positions.
Thank you. Not that young anymore.
But when comparing with me, it's true. Okay. I have a simple question, Marco, about hybrid construct that you are developing, because we are trying to doing the same, and we are facing with some challenge related with the combination between the PCL or other thermoplastics and hydrogels, and with incorporation of the cells. Can you explain us how you are dealing with this?
Yeah, I think you're absolutely right, Nuno. And obviously, when we work with the combination of thermoplastics materials that are printed using temperature, obviously that can have an impact on the viability of the cells that we then incorporate with the hydrogels. We're doing that in two ways. One that we are much more interested is the alternated deposition of polyester ureas and the cell-laden hydrogels. And that is great from an automated point of view. And if we want to seek the translation of that, that is fantastic. But it strongly impacts on the production time, because you need to allow enough time for the thermoplastic to cool down before you actually deposit the hydrogel. I think the most viable one for us is actually to first build the thermoplastic and then just cast the hydrogel within the system. So we are exploring those two. The one that allows us much higher cell viability and maintenance of cell phenotype is the construction of the scaffold, the thermoplastic scaffold, and then just the injection of the casting of the cell-laden hydrogel into the pores that are available within the construct. That is what gives us the best cell viability and function, especially with pluripotent stem cells that are very sensitive to any changes in the environment around them.
Okay, can I put one more question? Okay. My concern is related with in situ printing of the cells. Because if we try to print it PCL combined with hydrogel and online printing, cell online printing, we are facing with some concerns about the when is it more appropriate to do the incorporation or the printing of the cells. Here we are trying to optimize the time in order to cool the PCL to achieve an appropriate temperature to incorporate the cell. But at some times it's not so easy because you need to print the different layers with the first layers with a high temperature to have a good mechanical properties of the construct also, and it is a balance that is difficult to achieve. Can you share with us something about that or your knowledge about that also?
Yeah, I guess it's not just you facing those problems. We also face them, and I think a lot of people working with these hybrid structures, they also face the same problems. I think there are ways around that, and I think the use of SLAM, this suspended fluid gel, allows us to control that a bit more, because if you have a bath that will allow you to control the temperature and the diffusion of the heat from the layers of the thermoplastic, you have a much better control over the viability of the cells, and that's what we are focusing now. I can send you, if you want to, probably outside of this conference, I can share with you what we are doing, the formulation of the fluid gel to control, obviously not just the printing of low viscosity gels, but also to enhance this hybrid printing and to improve the viability. So that is something that we can do, and I'll be more than happy to share that with you.
Thank you very much. Thank you again.
Thank you, Nuno.
Any questions from anybody?
Can I make one? Sorry.
Yes. Yeah, please.
Hey, first of all, I would like to thank Dr. Marco for the inspiring and excellent presentation. And then I would like to, my question is related to your opinion about how to reach the clinics with these tissue engineering approaches. So if we are going to reach first using more adult stem cells like mesenchymal stem cells, or even these induced pluripotent stem cells that you described, and also about if we are first going to reach the transplantable devices or using these IPSs are more reliable in vitro models for targeting diseases. I would like to know your opinion on this issue. Thank you very much.
Thank you, João. I think that's a very, very important question. And I must say that, mesenchymal stem cell technology, it's a much more mature technology when compared to pluripotent stem cells. So it's very likely, because of the longer time that they've been around and the knowledge, the much in-depth knowledge that we have in terms of mesenchymal stem cell technology, that they will first reach clinical application, or we'll do that before pluripotent stem cells. However, this will never be an ideal cell source for clinical therapies. Mesenchymal stem cells are limited in terms of their differentiation ability, but also mesenchymal stem cells are limited in terms of their proliferation. So it will always be limited when we think of contexts where we need to treat a very large number of patients, where we need millions of cells. So from that point of view, these technologies will always be limited. And also, very often what happens with mesenchymal stem cells is that you implant them in a specific tissue site, like for example, in the cartilage. And what happens over time is that they will dedifferentiate into fibroblastic lineages. And you will not obtain, for example, hyaline cartilage, you will obtain a more fibro-like cartilage, which is not what we want in terms of regeneration. I think the pluripotent stem cells, and I think when you mention iPSCs, I think they are already extremely relevant in vitro. They will become, I think, very soon extremely important in terms of the pharmaceutical context, where we try to develop therapies and drugs and testing them personalized for specific patients. And I think once we are able to overcome some of the regulation obstacles that we have and ethical issues that we have around pluripotent stem cells, they will become also a much more regular and common technology in the clinical sets, because they allow us to, for example, we have a project in terms of wound care here in Manchester, where you can get adult stem cells, from a patient with a specific wound. We can reprogram those cells, and then we can actually develop therapies that are personalized for that patient in a clinical set. And I think that would be extremely beneficial. And obviously, pluripotent stem cells have an unlimited capacity of in terms of differentiation. And I think that will obviously be an added benefit when compared to mesenchymal stem cells. And I think that will probably be the future. If you ask me for a time scale, I wouldn't be able to answer that, because I think that will depend a lot in terms of the regulation and how we're going to be able to overcome that. But I think iPSCs are, from a technological point of view, ready to be included in the market, although there are still challenges in terms of the homogeneity of the populations that you're able to generate, because very often you don't have just pluripotent stem cells, you have other cells, and that will impact, obviously, in terms of the tissue that you're going to regenerate.
Yes, I think the main problem after we address the genetic instability of iPSs, I think they will be the main source. But also with MSCs, sometimes using the most used are the bone marrow mesenchymal stem cells, but other sources such as the synovial mesenchymal stem cells, they appear to have better results for cartilage tissue engineering. So,
absolutely, João. And I would also add that induced mesenchymal stem cells are probably going to be in the future the most reliable source of mesenchymal cells, cells that we derive from pluripotent stem cells into mesenchymal stem cells. I think that will allow us to have, they will still be classified as mesenchymal, although they are derived from pluripotent stem cells, and those will be probably a much more reliable source of cells in the future.
Yeah, I agree. Thank you very much.
Thank you, João.
Tomás?
Professor Mahadevappa, we are not listening to you. Don't know why.
Now it's okay?
Yes, it's okay now. Thank you.
Okay. Marco, thank you so much for giving a very challenging, lecture, and you have explained the strategies involved in the bioprinting and regenerative medicine. I hope audience are very much impressed with your lecture. Thank you so much for giving a wonderful lecture. Thank you very much.
Thank you very much, Professor Mahadevappa.
Yes, thank you very much. I request all the audience to vote for the lecture. I think your voting is required to identify the best presenter during the these 3 days, like 3-day lecture. So I think your voting is on, maybe it is on, just to check the website and give your voting to the what you call speakers. Thank you so much. Thank you so much. Finally, I thank the organizers for giving this opportunity to chair the session of the first day, session A. Now it is over. Now I will give it to the next session chair, Professor Vedamurthy. He will take charge and run the session B. Thank you so much. Thank you so much. Mitchell, anything I want to say? Mitchell, is it anything
Yes.
I want to say?
Okay, so we will restart at 2 o'clock.
Yes.
And the Zoom link for this afternoon session is the same as the one for this morning.
Okay.
So you can just remain connected to the Zoom session, go and have lunch, and then
Okay.
come back. You don't
Yes.
need to log out and log back in again. So
Okay.
Mahadevapa, thank you very much for very efficiently chairing this morning's session. It's very good
Yes,
to
yes.
see you well.
Thank you.
And
Thank you very much.